Hi, I'm Miss Hall, and this is Lesson 37, Properties of Rational Exponents, Properties of Radicals, Part 3. We'll begin by reviewing what it means to put an expression in simplest form. And an expression involving a radical with an index n is in simplest form when these three conditions are met. So the format we're going to see is, the nth root of some expression. Okay. The expression underneath the radical sign is called the radicand. The number outside the radical is the nth root. It's called the index. And let's review these three conditions. Number one, no radicand have perfect nth powers as factors other than 1. So if we have, let's see, the third root of 16x to the third, say, we want to pull out any perfect cubes, because it's the third root of this expression, to simplify it. So I know 16 can be rewritten as the third root of 8 times the third root of 2. And x to the third, actually I can take the cube root or the third root of x to the third, and that is just x. So I could simply write this expression as 2x, the cube root of 2. So that's an example of meeting the first condition. Second, no radicands contain fractions. I don't want, let's do the cube root of 1/27. I would have to take the cube root of 1 over the cube root of 27 to simplify, and I would get 1 over 3, right? The cube root of 27 is 3, and this simplifies to 1/3. Last condition, no radicals appear in the denominator of a fraction. So I'm running out of room. I will put this down here. I do not want, for example, 1 over radical 5. I'd have to rationalize the denominator by multiplying both the numerator and denominator by the same value. In this case, let me do a third root, or what do I know? I know a fifth root of, let me think about this. Okay. So let's say I have 1 over the fifth root of 16. And I want to rationalize the denominator. Well, my goal, let's see, is to get the fifth root of 32, because I know that that is 2, and I get rid of the rational denominator. And in order to get the fifth root of 32, I need to multiply the fifth root of 16 by the fifth root of 2. So I'll need to multiply the numerator and denominator by the fifth root of 2. I end up with the fifth root of 2 in the numerator, and my simplified version is the fifth root of 2 over 2. Example 7, writing variable expressions in simplest form. Write each expression in simplest form. Assume all variables are positive. So with A, I'm really concerned with condition 1 from the first part, which is no radicands have perfect nth powers as factors other than 1. And my approach to this is I'm going to rewrite this in x as an exponent, not the fifth root, but to the 1/5 or to the something fifth power. So my radicand, I'm going to write, is 4 to the first, a to the 8th, b to the 14th, c to the 5th. And I'm now taking my index 5 and putting these exponents all over 5. So this is equivalent to the starting expression. And now I'm going to simplify it. And what I mean by that is 4 to the 1/5. There's no simplifying there. I simply have 4 to the 1/5. But a to the 8/5, I can write this as a to the 5/5 times a to the 3/5. And I'm getting out a perfect fifth factor of a. A to the 5/5 is really just a, right? Similarly to b. I can rewrite this. The numerators need to add to 14, and I want to get rid of any perfect fifth factors. So b to the 10/5 and b to the 4/5, because b to the 10/5 is just b squared. And I have c to the 5/5, which that is a perfect fifth factor, and that is c. So I'm finally going to write this is a b squared c. Those are all the perfect fifth factors I was able to take out. And I still have the fifth root of 4 a to the 3rd b to the 4th. And that is simplest radical form. ab squared c, fifth root 4 a cubed b to the 4th. B, we have simplifying this expression where I have x over the 3rd root of y to the 8th power. I cannot have a radical in the denominator, so that's what's being violated in B. Let me rewrite this again as an exponent. This would be y to the 8/3 power. Now I want to multiply this by something so I get y to the 9/3 in the denominator, because I know that y to the 9/3 is just y to the 3rd, and then my denominator is y cubed. It has no radical in it. So what I need to multiply the denominator by to end up with y to the 9/3 is y to the 1/3. And I must multiply the numerator by the same. And so I get x, y to the 1/3. And I can write this as x cube root of y over y cubed. Lastly, example C. I'm going to choose to rewrite this as 14/2 times x over x to the 3/4 times y to the 1/3 over, there are no y's in the denominator, so I could put a 1 or I could put y to the 0 power. And z to the 0 power, because there's no z's in the numerator, or just 1, over z to the -6. So I lined up like terms. Keep in mind this is just a big multiplication. If you multiply the numerator, you'll end up with the original expression. You multiply the denominator, end up with the original denominator. And now I can simplify 14 divided by 2 is 7. When you are dividing with the same base, you can subtract the exponents. So x to the 1st power, I can write as x to the 4/4, and then subtract 4/4 minus 3/4, and I'll end up with x to the 1/4. Y, and I'll subtract the exponents. 1/3 minus 0 is just 1/3. And z, I'll subtract the exponents. Z to the 0 minus -6 is z to the 6th power. And just double check. Yep. This is my final answer. I have simplified expression C. Okay, I'm going to rewrite A as 2 to the 1/3 times a times a. The numerators add to 13, and I take out as many multiples as 3 as possible, so 12 and 1, because that makes a to the 4th. For b, just b to the 3/3, that is b. And c times c, where I have it over 3/3, I get 6 and 2, because this is c squared. And now putting it all together, I have a to the 4th b c squared cube root of 2 to the 1st, which is 2, a to the 1st, which is a, and c squared. Okay, b. I will write this as 16/8 times x over x to the 2/3 times y to the 1/3 over y to the 0 times z to the 0 over z to the -4th, which is 2x to the 1/3, right? I'm can rewrite x to the 1st as x to the 3/3, and then I can subtract the exponents. Y to the 1/3, z to the 4th. Now I've simplified both expressions.